Hello and welcome to this lecture on gas chromatography in our series on chromatography. And we'll be covering the introduction to gas chromatography. We'll also be talking about some of the methods used in gas chromatography. And we'll be continuing on to look at detectors and method development. So as an introduction, we will be looking at several different factors. The mobile phase, which is going to be our carrier gas in gas chromatography. It's kind of like the solvent, which will carry our analyte through the chromatographic instrument. We'll also be talking about whether the analyte requires, this requires the analyte to be naturally volatile or that it can be converted to a volatile derivative. Gas chromatography is useful in separation of small organic and inorganic compounds. And then in addition to that, as usual with chromatography, we have a stationary phase. So the stationary phase is usually a gas-liquid partition chromatography. So we've got a non-volatile liquid bonded to a solid support. So oftentimes this could be a long chain hydrocarbon, or it could be a derivatized hydrocarbon of some sort. Gas solid chromatography. So typically we're using underivativized solid particles. And then we've got a bonded phase gas chromatography. So this is a chemical layer chemically bonded to a solid support. So here are some potential solid layers. We've got here a carbon layer and fused silica. And so these can have interactions with our mobile phase, and that can result in the chromatographic process taking place as we look at how the analyte will be adsorbed onto the surface of these solid or stationary supports. So in our gas chromatography machine, we have an instrumentation process. So we have a volatile liquid or gas, which is injected through a septum into a heated port. And the sample then rapidly evaporates and then is pulled through the column with the carrier gas. The column is then heated to provide sufficient vapor pressure to elute the analytes. So if it's not heated, there's a chance that we could have some condensation happening inside of the column, and that would obviously stop our elution process. It would stop our separation process. The separated analytes then flow through a heated detector for observation. So here's a schematic of a gas chromatography instrument. So we have here our silicon rubber septum. So this is where we would inject it. So in the injector port, so we go through the septum, we'd inject it using a needle, and then the syringe containing our analyte would be passed through here, and then the heat of this injector oven would volatilize our analyte, and then this would be carried through our carrier gas through the column. Now, of course, our analyte must be volatile, at least at the temperature of the injector oven. Otherwise, we won't end up with any of it entering the carrier gas. And then, of course, after it's passed through the columns can be of different lengths, hopefully sufficiently long enough that we've been able to get adequate separation. Then it will exit out of the column oven, and the response will be detected by a kind of a detector, which is also going to be heated for the same reason that we don't want a condensation happening inside the instrument, because this would result in us needing to do some maintenance to the machine potentially. And then, of course, the computer is what we'll use for our observation. So commonly used columns in gas chromatography are open tubular columns. So these are basically just tubes that have a coating along the outside wall of the column, which is going to have different properties, and those different properties can be tuned to what we need in our specific use cases. So these columns are commonly used in gas chromatography, and they offer higher resolution, shorter analysis time, and greater sensitivity, but they have low sample capacity. And increasing the resolution typically means that we need to have narrower columns. And this is because by having narrower columns, we're introducing more potential collisions of the analyte with the walls of the column, and this will result in potentially more adsorption processes, which will hopefully increase the resolution. And the resolution is, of course, proportional to the square root of n, where n is the number of plates, where n increases directly with column length. So this is from plate theory, which you will hopefully have seen in our earlier series on chromatography. So it's easy to generate long, tens of meters of lengths of narrow columns to maximize resolution. So this is just kind of what a column looks like. It's just a big coil of very narrow tubes, which are lined with something, some sort of polymer usually, or it could be carbon, could be silica. It just depends on what your analytes are going to be. So here's an example of changing the diameter of a column and what can happen. So on the left-hand side, we have a decrease in tube diameter. So here it's a 0.32 millimeter diameter, and here it's a 0.25 millimeter inner diameter. And you can see that we have improved resolution between the peaks. Now, 1, 2, and 3 are still not very well resolved, but at least the resolution is better. And you can see that by continuously sort of decreasing the diameter of these tubes, you could improve resolution. But one other thing that we should notice is that the time of elution has changed. So the elution time has taken longer. It's gone from just under 2 minutes to just over 2 minutes for elution of all of the components. And so this is something that needs to be considered as well. So whilst we can also improve resolution, we're also increasing the length of time it takes for the elution to fully happen. On the right-hand side, then we have an increase in column length, and this also increases resolution. And you can see that going from a 15-meter column to a 30-meter column to a 60-meter column continuously increases the resolution. And in fact, at the 60-meter column, we have already got very good baseline separation and good resolution that could be used for adequate detection and quantification of our sample. However, of course, it comes with the same sort of caveat. The longer your column is going to be, it's going to take longer for your analytes to be eluted through the column. And so you can see that initially, of course, it's under 2 minutes, but as we increase the column length, we have an increase in time. Another way of increasing resolution in open tubular columns is to increase the stationary phase thickness. And so this will hopefully increase the resolution of early eluting compounds. So on the left-hand side, we have the elution of these 7 compounds and a 0.25 micrometer thick film coating on the inner surface of our column. You can see here there's poor baseline separation. We can see that the peaks are there, so we could qualitatively analyze this. However, the peaks are overlapping too much for us really to be able to quantify how much we have of each one of those components. On the right-hand side, however, we've seen that by increasing the thickness of the film from 0.25 micrometers up to 1 micrometer, we have improved separation. Now, there's a little bit of asymmetry that's creeped into the peaks, but we have got reasonable baseline separation here, and we can see that the resolution has improved. So also this increase in capacity factor and reduces peak tailing, but also decreases the stability of the stationary phase. So the choice of liquid stationary phase. So this is kind of based on like dissolves like. So it depends what kind of analyte that we have, the wall or which column we should have, or which stationary phase we should have on the walls of our column. So for example, if we have a polar analyte, typically we want a polar stationary phase. So non-polar columns for non-polar solutes, strongly polar columns for strongly polar compounds. To reduce bleeding of the stationary phase, we typically bond it covalently to the silica. So that means that it's liquid-like. It's not really truly liquid stationary phases, but because of that problem, if it was really a liquid, we would bleed some of the coating out of the spectrometer, which would not be very good. You can, of course, covalently cross-link to itself, depending on what the liquid would be. And over here on the right-hand side, we can see a couple of different stationary phases. We have stationary phases for non-polar analytes. We have stationary phases for intermediate polarity, strongly polar, and strongly polar here, and different temperature ranges for working temperature ranges for those. That's largely because if we go above those temperatures, we might start to actually degrade the coating of the tube. The stationary phase might actually start to be destroyed. So packed columns then offer greater sample capacity and improve resolution by using small uniform particle sizes. So the broader peaks, longer retention times, and less resolution is going to be observed. So if we've got like an open tubular column, so this is the columns that we've been talking about where we have these narrow tubes and then we have a coating on the tube, but the interior of the tube is actually going to be empty. So it's going to be a void through which the gas can pass. That will give us narrower peaks, but it does mean that we can't use as much sample. Whereas a packed column is probably more similar to what we're familiar with in liquid chromatography, because the whole column is packed with whatever our stationary phase is. It does, however, result in much broader peaks, but it does allow us to increase the amount of sample that we are putting into the column. You can see here that as well as that, the elution time is much longer for a packed column than it is for an open tubular column. So packed columns have the major advantage and use is in industrial preparation or industrial purification, because those open tubular columns, they have low sample capacity. So it means that it takes a long time before you would get a significant quantity of something. And typically in industry, most compounds are produced in large scale to improve profits and so on. So industrial scale purification is usually on the kilogram or greater range. If we used an open tubular column, it could take a very long time to obtain that amount of analyte. And so here's like an example of an industrial separator for an oil refinery. So the oil refinery, this separates the fractions of oil for petroleum products. You've got the different temperatures throughout the column, and they rise up depending on what they are. And here's, for example, a 500-liter chromatography column. So retention time or index, we've covered that as well before. So the order of elution is mainly determined by volatility. So less volatile is going to be the most retained. Polar compounds such as alcohols are the least volatile and will be the most retained on the gas chromatography system. And the second factor is the similarity in polarity between compound and stationary phase. So over here on the right-hand side, we have a look at different components and parts of our gas chromatography system. So the analytes, just sort of for your reference, we can go from non-polar to weak intermediate polarity, strong intermediate polarity, and strongly polar. And so that's going to be important for choosing our stationary phase. It's going to be important for looking at our system in general and our method development. So the retention index can be used to describe column performance. This can manipulate or adjust retention time by changing the polarity of the stationary phase. We can use these retention time differences to classify or rate the column performance and compare relative retention times between compounds and how they change between columns. And this can be used to identify unknown components of our system. So it would mean that we can sort of like try to understand maybe the particular elution times based on how they are held by our system. So you can see here on the right-hand side, we've got the two different columns, and we're looking at the different elution times and how they change. So for example, you can see that on the left-hand side, the peaks for the peaks for 6 and 9, so butanol and pentanol, so alcohols. These are going to be much longer in the right-hand column than in the left-hand column. And this is presumably because of their greater affinity for the stationary phase if the column has been changed. And as a result, we see that there is now this greater retention time. So it takes longer for them to be eluted. Some of the other orders don't really change too much, although some get shorter and some get longer. So the retention index is based on the difference in the number of carbons for linear alkene and the corresponding retention times. So we've got I is the index, and that's equal to 100 times the product of this term. So that's n plus n minus n. So it's the difference between the number of hydrocarbons, log of the retention time of the unknown, minus log of the corrected retention time for the n. So the smaller number of hydrocarbons, or carbon, sorry, and then all over log of the corrected retention time for n, minus log of the corrected retention time for small n. So this provides a mean to compare the performance of different columns. So the retention index will change based on the polarity of the stationary phase. So the stationary phases increase in polarity going this way, and we can see how the different analytes are going to be affected by that. So you can see that an increase in polarity is going to change the retention times of these. Temperature programming can also be utilized to improve column efficiency. So if something is not particularly volatile at a certain temperature, by increasing temperature, you're going to see a difference in the volatilization. So we're going to see how that can improve resolution. So in the top, we have a series of hydrocarbons being eluted in a column, which is isothermal. So basically meaning it's held at the same temperature throughout. However, in the second one, we're using a temperature gradient, which is programmed to increase the temperature gradually, which means that because these hydrocarbons have different volatilities, with increasing carbon length, typically what we see is a decrease in volatility. So that means we need to increase the temperature in order to elute them properly. So we can see here that initially, of course, we get the complete elution of short chain hydrocarbons, or at least short chain for this mixture. And those then come out sequentially. So as we increase the temperature, we see that we get different carbons of different length. And what's being highlighted here is that for an isothermal 150 degrees Celsius, we have this very bad fronting problem with our carbon 14 and carbon 15. It also takes very long for them to come out. In fact, we don't really get anything out beyond carbon 15, even though the sample contains many other hydrocarbons. And this is because of the reduction in volatility of those hydrocarbons. And so what we see is just this is a poor choice for the separation of this system. So temperature programming can be used to improve column efficiency. Temperature is raised during the separation. So this is gradient heating. So you can change gradients over time. This one was programmed temperature at 8 degrees per minute, but you could ramp that up if you felt that a method would be better served to have it faster. Maybe after 100 degrees of heating, it changes to 10 degrees per minute or something like that. And so this increases solid vapor pressure, of course, and decreases retention time, which means that the whole process or the whole elution happens much faster, maybe a third. It takes a third of the time, and we elute everything with the temperature gradient. But with an isothermal system, it takes a very long time, and we don't even elute everything. Pressure programming then, so this is going to also have an effect on our efficiency of the column. So pressure programming can improve column efficiency. So by increasing pressure, we increase the flow of the mobile phase, so the linear velocity of the mobile phase basically. So if we increase the flow, typically we decrease the retention time. Pressure is rapidly reduced at the end of the run, and time is not wasted waiting for the column to cool, and this is useful for analytes that decompose at high temperatures. So the Van Deemter curves indicate the column efficiency is related to flow rate, so that's right. So the maximum efficiency is not necessarily at the highest linear velocity. So the maximum efficiency is usually at the minimum of the Van Deemter plot for a particular linear velocity. The carrier gas, there's three major or main types of carrier gas. There's nitrogen, helium, and hydrogen. So helium is the most common, and it's going to be compatible with most detectors. It gives a better solution because it gives smaller plate heights, and solutes typically diffuse rapidly, and the smaller mass transfer term. So it's also an inert gas, so it's typically not going to really react with any of the analyte species, so you don't necessarily have to worry about that. Nitrogen, however, has a lower detection limit for a flame ionization detector and has lower resolution and solute diffusion rates. Hydrogen produces the fastest separations, can catalytically react with unsaturated compounds on metal surfaces, cannot be used with mass spectrometers because it forms explosive mixtures with air. It offers better resolution and smaller plate heights. Solutes diffuse rapidly because there's a smaller mass transfer term, or meaning a smaller mass transfer term. So the flow rate increases from nitrogen to helium to hydrogen. And the diffusion coefficients are from hydrogen is larger than helium, which is larger than nitrogen. So then the way that we inject the sample into our gas chromatography instrument is going to change some of the resolution and the quality of the chromatogram that we get out at the end. So one way to do it is through sandwich injection. So this separates the sample with air bubbles and solvent. So for example, we have air, then solvent, then air, then sample, then air again. And so this air bubble prevents depletion of most volatile compounds before sample injection is complete. So there's a barrier between the oven and the sample during injection. The solvent is used to push out the sample, but the bubble prevents mixing. The final air bubble pushes out the solvent. So gas titrate range is required for gas samples. An injection volume is typically 0.1 to 2 milliliters. So at the injection port here, sample is injected rapidly in under a second through the septum and into the evaporation zone, which is here. The injector temperature is kept high at around about 350 degrees Celsius for fast evaporation, and rapid gas flows carry the sample to mixing chamber for complete vaporization and complete mixing before entering the column. So it's going to happen here. So we're going to get mixing in here and heating in here. So the split injection delivers only around about 0.2 to 2% of the sample to the column. So this is a second type. So we've done sandwich, now we're doing split type. So the split ratio of 50 to 1 to 600 to 1. And so how much of the sample is actually discarded and how much of it is actually made use of. So for samples where analytes of interest are greater than 0.1% of the sample, so quite concentrated. So the best resolution is obtained with smaller amounts of sample, so less than 1 milliliter with less than 1 nanogram of each compound. So this gives around about 0.5 milliliters of gas volume equivalent. So this is not quantitative and the split is not constant. So split type injection is really useful only for qualitative analysis because it's hard to make sure that the split ratio is exactly the same every time. So here is the setup of an injector for split injection. So we insert our sample through the syringe, through the septum, then we have a gas flow in here, and then we split some of it. So some of it will pass into the column and some of it will also vent out. And so the ratio can be changed. So after mixing, pressure regulator controls the fraction of sample discarded. So basically we change the pressure in here, and by changing the pressure, we force because the split vent is open, it's easier for the sample to pass out that way than it is to pass into the column. So this means that more of our sample is vented than it goes into the column, but by changing the pressure in here, that will also control how much of it is actually vented. So splitless injection. So this delivers around 80% of the sample to the column. For trace analysis, where analytes of interest are going to be less than 0.01% of the sample. So we're going to need large volumes injected over a few seconds, and no mixing chamber or split vent is present. So the injection temperature is lower, 40 degrees Celsius below the boiling point of the solvent. So injecting larger volume, we don't want broad peaks. So the lower temperature traps the solvent in a narrow band at the head of the column, and then we raise the temperature down here to volatilize the sample and start separation. Solvent trapping significantly improves the performance of splitless injections. So the initial lower temperature of the column during injection keeps the larger volume into a narrow band. Chromatography is initiated by raising the column temperature. So this volatilizes the analyte. And then cold trapping is used to condense the solutes in narrow band at the beginning of the column by using an initial temperature 150 degrees below the boiling points of the solutes of interest. So this is a comparison of using solvent trapping without using solvent trapping. So you can see without solvent trapping, we have a big problem with tailing. It means that we can't really use our peaks qualitatively, but with this solvent trapping, then we're able to improve the resolution considerably, and we can see that we have nice symmetric peaks. On column injection then, so this is injection pretty much directly into the sample. So 100% of the sample is delivered to the column. So you can see here's the column start, and the gas syringe is directly attached to the column. So this delivers 100% of the sample to the column for samples that decompose above their boiling points, and the solution is injected directly on the column, and warming the column initiates chromatography. So the lower initial column temperature is used to prevent sample decomposition, and so we raise the temperature to volatilize the sample and start separation. So we don't want the sample to decompose before it gets into the column. So detectors in gas chromatography. So the detector we use is going to change based on whether we have qualitative or quantitative analysis. So one thing that you can often add to gas chromatography instrument is a mass spec or Fourier transform infrared detector to the column. So a common form of spectroscopy is GCMS, so that stands for gas chromatography mass spectroscopy. So basically we do mass spectroscopy after our gas chromatography. And so this has the advantage of being able to separate our solution into into its individual components through the chromatographic process. So that means that we can then do mass spectroscopy on each individual component of our mixture. And then oftentimes the software has a library of spectra, which can help us identify the compounds, although it's not foolproof. Compare retention times between the reference sample and the unknown. So we use multiple columns with different stationary phases, and we co-elute the known and unknown and measure changes in peak area. So the area of a peak is proportional to the quantity of that compound, and so that's very nice, and that's why we want the peaks to be well resolved, because it means that we can use this technique to determine maybe the quantity of something that we've produced or the quantity of something we have extracted from something else, to just sort of quantify the usefulness of whatever research we have done. And so this is the area of the Gaussian peak is equal to 1.064 times the peak height times the width at half maximum. And so that peak area can be, if we have a series of standards, we can create a calibration curve. Peak area increases proportional to concentration of standard if unknown standard have the identical retention times. This is the same compound. So detectors, so thermal conductivity. So this measures the amount of a compound leaving the compound by its ability to remove heat. Helium has a high thermal conductivity, so the presence of any compound will lower the thermal conductivity, increasing temperature of the filament. As heat is removed from the filament, the resistance of the filament changes, This causes a change in electrical signal that then can be measured, because ultimately, most of the time, what we're doing is we're measuring electrical signals. Response to all compounds, so it's pretty much universal, because every compound will reduce more or less the thermal conductivity of helium. The problem is it's not very sensitive. So you need quite a lot of your analyte before you see a significant deviation in the current or the electrical signal. And so this is all related to Ohm's law, where the potential is equal to the current times the resistance of the filament. And so this is what the detector looks like. So there's a gas flow in, then there's an electrical circuit with a filament. And this is the filament which will basically respond to the components in the mixture, and then the gas flows out. Flame ionization. So the mobile phase leaving the column is mixed with hydrogen and air and burned in a flame. So carbon present in eluting solutes produces CH radicals, which produce CHO plus ions. Electrons produced are collected at an electrode and measured. This responds to almost all organic compounds and has good limits of detection, around about 100 times better than thermal conductivity detector, and is stable to changes in flow rate and common mobile phase impurities such as oxygen, CO2, water, and ammonia. So this is the process by which a hydrocarbon reacts with oxygen to form these CHO plus an electron. So the amount of electrons produced will produce an electrical signal which can be measured. The fourth type of detector is an electron capture. So this is sensitive to hydrogen containing and other electronegative compounds. So based on the capture of electrons by electronegative atoms, compounds are ionized by beta rays from the radioactive 63 nickel. So there's the nickel 63 foil inside of our electron capture detector. And this is extremely sensitive, so it can detect concentrations of as low as 5 femtograms per second. So steady flow or steady current flow of electrons is disrupted by compounds with a high electron affinity. And so this will change the electronic nature and of the internal electron capture detector. So then the last one is the gold standard, really, the one that everyone wants is more or less. I mean, there might be some niche use cases for the other ones over mass spec, but really mass spec is the one that everyone wants. So typically, as I said before, this is a coupled technique. It's called GCMS. This is detector of choice, but mass spectroscopy detectors are expensive. Is sensitive and provides an approach to identify analytes. So basically, you've got usually most of the time it's sufficient, gives sufficient information to actually be able to identify the analytes, because if they've been resolved properly, then you can get the mass spectrum at a particular point in time, which represents just one analyte. So this is selected ion monitoring. So monitor a specific mass to charge ratio compared to scanning over the complete spectra, and it simplifies a complex chromatogram and increases sensitivity by around about 100 to 1,000 times. So other detectors also exist, and so these are typically for particular elements that you're interested in finding. So they respond to a limited class of analytes. There are modifications usually of previous detectors that we've seen. So a nitrogen phosphorus detector is a modified flame ionization detector, so that is extremely sensitive to compounds containing nitrogen and phosphorus, and these are important for drugs and pesticides. And so these are the kind of modifications that you might get in law enforcement, especially. Whereas the flame ionization detector was sensitive to hydrocarbons predominantly, by changing this for an NPD, you are able to detect with high sensitivity nitrogen and phosphorus in compounds. Flame photometric detector, so this measures the optical emission from phosphorus, sulfur, lead, and tin, and other select elements after passing the sample through a flame. So this is also a modification of a flame ionization detector. Photoionization detector uses a UV source to ionize aromatic and unsaturated compounds. Electrons are measured using an electron capture detector. And then finally, the last sort of other detector is a sulfur nitrogen chemiluminescence detector. So this collects exhaust of the flame ionization detector. So it's coupled with the conventional flame ionization detector, and any sulfur and nitrogen atoms which are volatilized from the compound will be converted to sulfur monoxide and nitrogen monoxide. Then these can be mixed with ozone to form an excited state of sulfur dioxide, which emits blue light, and sodium or nitrogen trioxide, which both of which can be then detected and help use to quantify the amount of sulfur or nitrogen in our sample. So sample preparation. So this is used to transform the sample into a form suitable for analysis. So we want to extract, concentrate, and remove interfering species or chemically transforming species. So we want to avoid derivativization inside of the column. One of the ways that we can do this is through solid phase microextraction. So we extract analytes from the complex mixture without solvent. And so this uses a fused silica fiber coated with a stationary phase. And so the stationary phase is similar to those used in gas chromatography. We then expose the fiber to the sample to extract compounds, and then inject the fiber into the gas chromatography to evaporate the analytes. So pierce the sample septum with a metal needle, so the needle goes in first, and expose the fiber to solution or headspace for a fixed time with stirring. Then we retract the fiber and withdraw the needle. Then we pierce the chromatographic septum with the metal needle. So this is the oven of the GC. And then we insert the same fiber into the hot fiber, expose the hot fiber to the carrier gas for a fixed time. The column is still cold. And then we retract the fiber and withdraw the needle. So that's a way of doing solid phase microextraction. So it means that we get relatively low concentrations, which hopefully should prevent saturation of our column. Another part in sample preparation is purge and trap. And so this removes volatile analytes from liquids or solids, concentrates the sample, and transfers to gas chromatography. The goal here is to remove around about 100% of the analyte. And so that's what it looks like over here. So we use bubbles to bubble purge the gas, using helium, of course, which is our standard, through the heated sample to evaporate analytes. Then the analytes are captured on an absorbent column, and then we connect this all through to the GC. And then we heat the column to 200 degrees Celsius to transfer the analytes to the gas chromatography column. Okay, method development in GC. So how do we choose a procedure for a particular problem? There are many satisfactory solutions to a particular problem. Usually it's a combination of multiple different factors, like which stationary phase, which mobile phase, how should I inject the sample. There are usually many options, and many of them will give good results. So it can be difficult to find the one which gives the best results. So the order in which a decision should be made on the method is as given. So the first thing is to decide what the goal of the analysis is. Are we doing qualitative analysis? Are we doing quantitative analysis? And therefore, after that, many of our questions will already have been answered. Then, of course, we need to make sure the sample preparation is correct, because ultimately, if we have a pretty dodgy sample, we're probably going to get a dodgy analysis result. Then we look at the detector, the column, and injection method. So the goal of the analysis is like, what do we want? Do we want qualitative analysis? Do we want to know what's in there? Or do we want to know how much of something is in there? The resolution versus sensitivity. So do we want to have well-resolved peaks, or do we want to be able to detect really small quantities of something? Precision versus time. So how much time do we have to do this measurement? Because ultimately time is money. The longer we spend on one analysis, the less time we have for other analyses. And so that can be problematic in a busy lab, whether that be a research lab or industrial lab. And then, of course, what is our interest in the specific analyte? And the second one is sample preparation. So, of course, we want to clean up a complex sample is essential. We want to make sure that there's no species which could interfere with the signal given from our analyte that we're interested in. We want to make sure that there's no potential for derivativization. There's no potential for reactions inside of the column, and so on. And ultimately, if we get garbage in, we get garbage out. So if we give a sample which is not suitable for the stationary phase, we may end up with a situation where we actually destroy our column if we choose the wrong things. Choosing the detector then, so we detect the specific analytes or everything in the sample. What are we looking to do? Do we want to only find something like, for example, in the NPD detector, we were only really interested in nitrogen and phosphorus, so we won't be able to detect other things like carbons and maybe other elements of interest. What's our sensitivity to that? Do we have a very low concentration of analyte, or is the concentration quite high? And then, do we want to identify an unknown? Like, do we not know what's in our sample? Do we not know what our analyte is? In which case, we would need a detector which can give us additional information, which can be used to actually understand our sample. And so this would be mass spec or IR. So then selecting the column, so we want to consider the stationary phase, the column diameter and length, the stationary phase thickness, because we want to match that to how we can improve the resolution. We want to match the column polarity to the sample polarity. So if the sample is polar or the analyte we're interested in is polar, the column should also be polar and so on. To improve resolution, remember that we can have a longer column, a narrower column, or a different stationary phase, but longer and narrower columns both increase the elution time and so therefore will reduce the throughput of our instrument. And then the last thing that we want to talk about is choosing the injection method. So the split injection is best for highly concentrated samples because it rejects a lot of the sample, depending on the pressure inside of the oven. Splitless injection is best for very dilute solutions. So this only really, this gets around 80% of the solution. So most of it will go into the column. And then on-column injection is best for the quantitative analysis of thermally unstable or unstable compounds. So that was an overview of gas chromatography. Thank you for watching and listening.